Okay, here we are moving into Chapter 7 on gases, an important topic for the history of chemistry, and we'll see a very famous name throughout this chapter. It will hit Amadeo Avogadro, and Avogadro's number was first approximated using gases, or at least the idea of that large a number was arrived at through gas laws. So clearly it's an important chapter, and hopefully one that feels a little more familiar to you after all those combining ideas from chapter 6 that got quite dense toward the end. Gases seems to be a little easier to manage. Hopefully you'll agree. In this first part of chapter 7 on properties of gases, things should feel very comfortable. This goes back to elementary school when you first probably started to learn about gases. So we'll start nice and simple for you, and we'll build our way up, and we'll get to some mathematical relationships and all that good stuff later. But for now, let's focus on the key properties of gases. So one of the reasons gases are so important is because they're so common. We don't see them generally. If you can see a gas, it's a gas you should get away from because colored gases are all toxic. Smokes are different than gases. So you know, smoke around a fire, it's not great for your health, but compared rather with the purple iodine vapor that will kill you pretty quickly, the smoke's not an immediate danger. So of the elements on the table, we've seen that a number of them are gases at room temperature, and those that fall into that category would be the entirety of group 8 or group 18, the last column on the periodic table, the noble gases. Gases is part of that column name, so it makes sense that all of those should be gases at room temperature and pressure. We've also got 6 of our 7 diatomics, right? Or I'm sorry, 5 anyway. Bromine and iodine we don't have included because bromine's a liquid and iodine's a solid, but at room temperature and pressure we have hydrogen, nitrogen, oxygen, fluorine, and chlorine, 5 of those 7 diatomic elements. And then finally, lots and lots of oxides of nonmetals. Usually when it's nonmetal combining with oxygen, we tend to think of gases as a product, but not always. So carbon monoxide, carbon dioxide, nitrogen monoxide, nitrogen dioxide, sulfur dioxide, and sulfur trioxide are a few common examples. Again, if we have silicon oxides, silicon's a metalloid, and we tend to get solids when we have silicon oxides on the other hand. Okay, phosphorus oxides tend also to be either gas or liquid or solid depending on the particular form made. But these are some very common gaseous compounds that we've encountered multiple times throughout the courses, particularly back in chapter 6. Gases are also a very topical concept right now because of the environmental concerns. So when we think about things like environmental or health issues, a lot of times, unfortunately, it's gases to blame. So methane is believed to be a major player in the global climate change. Chlorofluorocarbons have played an unfortunate role in depleting the ozone layer. That's actually a success story. We acknowledged there was a problem, and eventually we actually did something about it. Many countries banned the use of those CFCs, and things actually got better. It took a while, but that ozone hole is actually getting smaller rather than larger. So that's good news, and a key example of how getting the public behind science and doing something about it can yield results. Unfortunately, if we go back to methane and carbon dioxide and the global climate change, the public is still at odds, and certain scientists are still at odds about that, so we don't quite have the same support. Nitrogen oxides are a major component of smog in large cities and can be quite dangerous to venture out, particularly for young children and the elderly on those high smog days due to the damage those nitrogen oxides can cause. And then finally, volatile organic compounds, or VOCs as they're known. They were commonly found in paints and consumer products. And again, a nice success story where much of that has been replaced with less toxic components. A lot of paints today are mainly water-based. Some paint thinners still may have some volatile organics, but a lot of this has been replaced with safer, more environmentally friendly components. So that's good news, right? We should always be concerned about the environment and about human health, and we should be working as chemists or as nurses or as whatever your profession ends up being, working to improve health and safety for humans, for other animals, for the environment in general. One of the key reasons that gases have been studied for so long is that they behave themselves. Things aren't as complicated in gases because gases tend to act a lot like these hard billiard balls that we originally conceptualized them to be. So kinetic theory of gases has held for centuries now, and it consists of a few key ideas. First of all, the theory holds that a gas consists of very small particles, and those small particles are moving randomly at very high velocities. They have essentially no attractive or repulsive forces. This is why they can be treated like hard billiard balls. They sort of just bounce off of each other. They don't to any appreciable extent attract or repel each other with any additional force. It's just the sort of elastic-like collisions that they have. They have a very small volume compared to the volume of the containers they occupy, so there's a lot of distance between gas molecules, and that allows us to have some pretty good real gas behavior that subscribes fairly well with the theory. Finally, they're in constant random motion, right? And they tend to be moving pretty fast, so they don't have a whole lot of time to stick around and affect one another. And then finally, the last postulate here is that they have kinetic energies that increase with an increase in temperature. Temperature itself is a measure of average kinetic energy. So as temperature increases, it makes sense that the average kinetic energy of the gas particles will increase as well. Now, notice I said average. There are going to be some slower moving and some faster moving gas particles at any temperature, but the majority will be moving faster as the temperature of the sample increases. All right, so here we have a property of gas slide. So gases tend to be described in terms of four key properties. Pressure, which has to do with how many gas particles there are and how much force they're exerting against the walls of a container. There's volume, which talks about the space occupied by that gas. There's temperature, which we just mentioned in terms of average kinetic energy. And then finally the amount, the number of moles of the gas present. And so those four features are what we're going to spend the next several sub-chapter topics discussing. So table 7.1 there gives a nice summary of those properties that describe a gas and also the units of measure when we get into the math of chapter 7. Let's pause now for a learning check as we ease our way in here to chapter 7. So this learning check challenges us to identify the property of a gas, temperature, volume, or pressure that is described by each of the following. So choice A increases the kinetic energy of gas particles, choice B, the force of the gas particles hitting the walls of the container, and C, the space that is occupied by the gas. For each of those letters, just identify next to it whether we're talking about temperature, volume, or pressure. We have three letters and three properties, so it's probably pretty logical they'll each be used once. Go ahead, pause the video here, assign your properties, and then start it back up, and we'll see how you did. Okay, and there we have it. So as we mentioned, the kinetic energy of gas particles has to do with the temperature. The higher the temperature, the higher the average kinetic energy of those gases. For B, the force of the gas particles hitting the walls of the container, that has to do with pressure. That's actually the definition of pressure. And then finally, choice C, the space that's actually occupied by a gas is its volume. Hopefully that was nice and simple, and you're eager to move on to the next part of Chapter 7. If that's not the case, if you're struggling with these ideas or just having a little trouble getting your mind around one aspect, please do reach out to me, and I will do my best to get you on board.